Okay, chapter 15 is about chemical equilibrium. And what you'll see over the course of the next few weeks is that we have several chapters that are dedicated to equilibrium in different particular systems. And equilibrium is really one of the big topics of this whole Chem 1220 course. And so let's just introduce the idea of chemical equilibrium. We can have two different chemical reactions. 3H2 gas can combine with N2 gas, and that will produce NH3 gas, two of them. But we can also have this reaction. NH3 gas can decompose into N2 gas plus 3H2 gas. Both of those can and do occur in nature. And so if we consider a mixture that contains some hydrogen and some nitrogen and some ammonia, then both of these will be occurring simultaneously. Hydrogen and nitrogen will be combining to form ammonia. Ammonia will be decomposing down into nitrogen and hydrogen. What will happen is that the rate of this forward reaction will depend on the concentrations of hydrogen and nitrogen. And so as the reaction proceeds, the reaction rate will slow down as you get more product here and less reactant. Now similarly, we can consider the rate of this second reaction. If we start with a lot of ammonia, then that reaction rate will be fast. As that reactant gets consumed and we build up product, then the rate of this reaction will slow down as well. And ultimately what you're going to get is a mixture where the nitrogen and hydrogen the nitrogen and hydrogen combining to form ammonia rate is going to equal the rate of ammonia decomposing. Those two rates will become equal to each other, and so the concentrations will become stable. They'll become steady and unchanging. And that is what we call an equilibrium mixture. Equilibrium is when all of those reaction rates are equal to each other and the composition becomes stable. And you can see how we can reach this equilibrium mixture by starting with pure nitrogen and hydrogen. Give it some time and it will generate ammonia until it reaches a steady state. Or we could reach that equilibrium mixture by starting with pure ammonia, and eventually it will decompose, generating some nitrogen and hydrogen, and until it reaches that steady state, the equilibrium condition. If we were to consider the rate of reaction, if we start with pure ammonia, then that is shown in figure 15.2. The rate of the forward reaction, ammonia decomposing into hydrogen and nitrogen, will start very high, and as the ammonia gets consumed, then its reaction rate will slow down until it approaches some that equilibrium value. In the reverse reaction, the recombination of hydrogen and nitrogen to reform ammonia, that reaction rate will start at 0 because we have no hydrogen and nitrogen to begin with. But as the amount of hydrogen and nitrogen build up, then that reaction rate will increase until the forward and reverse reaction rates are equal to each other. Okay, so that's the idea of equilibrium. Perhaps it's not an unfamiliar idea to you. We can take both of these equations and we can combine them. They are just the reverse of each other, and so it's a little bit redundant. So we can say let's make it consistent with figure 15.2. So we'll say 2 NH3 gas goes to N2 gas plus 3 H2 gas. Only instead of having a reaction arrow that goes only forward, we'll do this double-headed arrow that indicates that it could go both directions, both forward and reverse. And this is an equilibrium. I want to stress that equilibrium is a dynamic state. Even though the concentrations of your reactants and products remain constant once you reach equilibrium, that doesn't mean that nothing is happening on the molecular level. You're still going to have ammonia breaking down, and you're still going to have hydrogen and nitrogen combining to form ammonia. It's just those two processes have equal rates, and so they balance each other out. And then also I want to point out that we could have written this the other direction. So we need to be very careful when we talk about equilibrium reactions. What's on the left side of the arrow we'll call reactants, and what's on the right side of the arrow we will call products. But someone else may have made the decision to write this equilibrium reaction in the reverse, and their reactants would be our products, and our products would be, and our reactants would be their products. And so you need to kind of be careful if you're talking about, say, the equilibrium reaction between ammonia, nitrogen, and hydrogen. Well, that's not enough information. You need to make sure you specify what are you considering the reactant. In this case, ammonia is the reactant, and nitrogen and hydrogen are the products. And while we can reach an equilibrium mixture from ammonia or from a mixture of nitrogen and hydrogen, hopefully you can see that if I just have nitrogen gas and I put that in a chamber, it is not going to be able to achieve equilibrium because it's missing its co-reactant. It's missing the other component here on the right side. And it's not going to be able to generate any NH3 whatsoever without the presence of some hydrogen. So if we go back to oops, sorry, I forgot to make it visible. There we are. If we go back to figure 15.1, we can reach equilibrium from either side of this reaction, but we must have at least all of the components of one side, or else the reaction can't proceed at all, and equilibrium will never be reached. See, this was a very short section. I guess that's it.